So thank you everyone for attending today. We really appreciate you giving up your lunchtime. We're really pleased to introduce and welcome Francesca Pianosi and Saskia Salwey from University of Bristol, who are talking today on the uncertainty of infrastructure modeling. So it's a project that is on DAFNI, and we're really looking forward to hearing more. So I'll hand over to you, Francesca, but just to say, please raise your questions in the chat, because at the end of Francesca and Saskia's talk, we'll then take some questions, and we'll wait until the end of the talk before we answer any of those questions, even on the Q&A side. So over to you then, Francesca and Saskia, welcome.
Thank you very much. Sorry for the late start. I'm Francesca Pianosi from the University of Bristol. Saskia Salwey, also from Bristol. We are working together on a project with the DAFNI team on bringing uncertainty and sensitivity analysis into the DAFNI platform. So it's very good to get the opportunity to give this seminar, share what our ideas are, what our plans are, and perhaps engage more with the user community going forward. So we thought a little bit how to structure the seminar. So what we're going to do is I'll give a quick intro on the methodology that we are talking about, focusing in particular on the reason why we believe it's important and useful to do uncertainty and sensitivity analysis of models. And then Saskia will go through a very simple example that hopefully is understandable and shareable reasonably easily on how we are planning to implement the methodologies in the platform on DAFNI. And then I think we'll stop there. And we have some extra slides that go into a bit more of the technical details of the methods, but maybe we can use them to answer questions if people are interested. Otherwise, we'll try to keep it as general and understandable as possible. So, of course, I don't need to convince you, I guess, that mathematical models are increasingly used to support and inform decisions in a variety of sectors. Here are some examples. I don't know if you live in the UK, you can access through a website information produced by a model on, for example, likelihood of flooding. Or the other example here is a European-wide model of the energy grid under different options of renewable sources development. This plot here just is something I always like to share. It's a report from the European Commission Joint Research Center looking at how many of the European Commission impact assessment have been supported by some form of modeling activities over the years. And what you see is this linear trend of continuous growth. But obviously, we all know also that model outputs are conditional on many uncertain assumptions. And broadly speaking, we can categorize this into two types. So there is a lot of uncertainty around system properties and drivers now at present day. And this is due to errors and gaps in the data that we use to build and run our models, and simplifying assumptions that we unavoidably have to make. And very often we don't really have a very strong way to test or check whether they are adequate or not. This is just an example, river flow data, which underpins the construction and use of, for example, those flood inundation mapping that I was showing in the previous slide. This is a variable that we measure reasonably well, and yet is a variable that even if we measure reasonably well, can easily have errors of the magnitude of 30, 40, even more than 50%. And that's in a country with a very well-developed Gaussian monitoring network like England and Wales. And then we have places, this is an example, the Congo Basin, this is not in the right proportion, is actually much bigger, and the dots are the very few points where any measurement is being taken. And then on top of it, when we use models to look at investment decision, what we typically want to know is the evolution of systems over long temporal horizons. And then there is obviously, unavoidably, lots of uncertainty around how the drivers of the system will evolve in the future. And this is a funny but very agreeable Danish proverb on making predictions about the future. And this is a picture that maybe some of you are familiar, which conveys very clearly this idea that when we build this very long modeling chain, then we have a propagation of all the uncertainties that go through these models. And so we end up, when we look at the final model outputs, having potentially very large and broad range of uncertainty around what might actually happen. So for models to be trustworthy and effective, we must ensure that we avoid spurious precision, that we are open about what is the level of precision that can be expected from a model. It's important to be able to identify the key sources of that uncertainty so that we can know when a model stops being valid, or if we want to improve the model and increase its precision, where do we start? And then also, if we use models to appraise different investment options, different design, we might want to look at what are options that perform well enough across a large range of future possible scenarios, and that's what we mean by robustness. So our claim, somehow the idea underpinning our project, is that uncertainty and sensitivity analysis provide a generic methodology to explore these questions. By generic, I mean model-independent methodologies that can be applied to models with different characteristics in different sectors. And so that's the idea of why also we would like this to be available on DAFNI. And just to clarify the terminology I use, when we talk about uncertainty analysis, what we are talking about typically is uncertainty quantification. So asking the question, what is the range of variability in the model outputs, given our level of uncertainty in the model input and underpinning assumptions? And instead, when we talk about sensitivity analysis or uncertainty attribution, what we mean is finding out what is the relative contribution of different uncertain inputs to the final uncertainty variability of model outputs. So it is about attributing back the uncertainty to its sources. And also, as a matter of clarification for those who might not be totally familiar with some of the terminology we use in this seminar, we are focusing on so-called global approaches. To understand what a global approach is, perhaps it's easier to start by thinking of what is a local approach. So a local sensitivity analysis is an assessment of the effects of varying the uncertain inputs of a model one at a time around a baseline point. So in this example, we might have 5 input, we vary input number 2, and this is the impact on the output. And then we go back to our baseline, the black dots, and we vary input number 4, and this is how much the output vary. And so what we see is that for the same amount of variation in the input, we have a much larger impact when we vary x2. So there is high sensitivity to that one, and perhaps instead there is another input where same amount of variability does not actually have a significant impact on the output. Now, the problem with this approach, the limitation of this approach, is that we do not know to what extent our sensitivity assessment might be different if we were to do the same analysis, but starting from a different baseline. And very often with a model, we don't have a meaningful baseline. We know that input might vary within certain ranges, within some list of possible options, and that's all we know, but we don't have any particular combination of those input, which is the one we trust most or are most interested in. So this is the case where we might want to do a global sensitivity analysis, where the idea is that we look at the effects of varying all the inputs at the same time across their entire variability space. This will obviously lead to a distribution of possible output values, and then the question of sensitivity of a global sensitivity analysis is, where is this uncertainty mostly coming from? So in a nutshell, these global approaches are based on repeated executions of a model against different input combinations, and then a statistical analysis of the input-output data set that we built in this way. So for those who are familiar with this terminology, this is called Monte Carlo simulations. We need to characterize the uncertainty in the input, for example, with a list of possible values or ranges of variability. We sample a certain number of combinations from of those input, and we execute the model against each one of them. And then once we have created this data set, this sample of input and output, we can calculate distribution or confidence intervals for the output, and this is the uncertainty quantification. Or we can use some statistical techniques to calculate sensitivity indices. So numbers that tell us what is the contribution to the output uncertainty from each of the input that were sampled. And again, for those who might have heard of this, there are different techniques that can be used to perform these sensitivity calculations. For example, a very popular one is variance-based or the elementary effects method. I'm more than happy to give more details of how these different methods work, but maybe we leave that for question time. Instead, very briefly before passing over to Saskia, what I wanted to discuss is a few examples of how people have used uncertainty and sensitivity analysis, and ultimately, what is this useful for? And it's a range of different applications that one might be interested in. So a very typical example is doing sensitivity analysis as a way to support the calibration of a model. So very often we have models with a lot of parameters, and if we have some data, we will do a calibration, meaning we will have some automatic algorithm to find the value of the parameters that maximize the model accuracy, so the fit to the available data. Very often these tasks are very complex and time-consuming, especially if we have a lot of parameters or if we have a complex model that is a bit slow to run. So the question here is, can we identify the parameters that mostly control the fit to data and therefore should be the focus of a computationally expensive calibration? So an example from hydrology, this is also similar to the example that Saskia will use. We have a model that is used to predict river flows, and then we have some observations of river flows, which are the blue dots in this plot. We can run Monte Carlo simulations, so instead of having one time series of predicted flows, we have an ensemble of time series, which is all these gray bands. So this is the uncertainty quantification part. And then we ask the question, what are the parameters that mostly contribute to that variability of river flow prediction? And the answer is on the right-hand side, where we have a plot of all the parameter and these sensitivity indices So where the longer the bar, the more influential a parameter is. And what we see in this example is that actually out of over 30 parameters that are present in this model, only 4 or 5 are really significantly controlling the prediction accuracy. So that means that any future calibration efforts can be focused on this parameter only, and then becomes much more tractable and feasible. Another example of using this kind of techniques is to have some evidence for prioritizing efforts for reducing uncertainty. Because if we can identify which sources of uncertainty influence the precision of the model output the most, then it means we know where efforts for improving the model or the input data, the quality of the input data, will have the most beneficial effect towards improving precision. Or put the other way around, we know where we should not waste our time and resources, because even if we improve that aspect of the model or that particular input data set, it wouldn't make much of a difference. So I'll show an example of a recent work from some colleagues at the Met Office looking at risk assessment. This is a model that in particularly look at the risk of losing days of work due to heat stress. Like most of this risk assessment model, the model is essentially is a combination of many of different parts. So there is a component to calculate the hazard, so the future temperature peak. There is a vulnerability component that maps temperature into damage losses, and then there is exposure map, so any spatial information of where people or assets will be exposed to those hazards. And so what we did together in this work is we looked at various sources of uncertainty in the hazard, vulnerability, and exposure component, and trying to quantify the uncertainty in future risk, and also the sources, the key control of that uncertainty. So in this plot here, for example, you can see future risk under different warming level scenario, and using different hazard maps, so different product to calculate future temperature. And what you see in a nutshell is obviously that with increasing warming level, we have greater risk, but also that we have a greater uncertainty across different hazard maps. The sensitivity part also was particularly interesting in this case. What we did is we quantified the sensitivity of this risk metric to the input uncertainty. So there are different parameters or choices that need to be made in the hazard, exposure, and vulnerability component. And again, we have a sensitivity index. In this case, the higher, the more important that particular source of uncertainty. And what we see here is that, for example, quite predictably, not surprising, the choice of the warming level is the most influential factor on risk. That's reasonable and expected. But the interesting part is that the second most influential control uncertainty source is the parameterization in this vulnerability component, which has all to do with our inability now to represent a very complex process there. And that is a component that very often we overlook a bit. And what we find out that this is, for example, much more important than than the choice we make to bias correct future climate predictions, which is instead a task where we often invest quite a lot of work. So this is basically telling us unless we are able to reduce a bit the uncertainty in that particular component, it's not particularly useful or beneficial to invest a lot of modeling activities on these others, because this is the bottleneck in terms of what control our understanding of future risk. The very last example I wanted to mention, which kind of also builds up on this a little bit, is moving more and more towards thinking about the way we evaluate model and the way that we ensure that models are suitable for the task of supporting decisions. So one question that we can ask for with this kind of global sensitivity analysis approaches is, what are the dominant controls of the model outputs? And in particular, are model outputs sensitive to decision-relevant input? And the reason why this is important is because, again, if we can't establish that, and if we find actually that outputs are more strongly controlled by uncertain assumptions or parameters than they are by policy or scenario inputs, then this is telling us that the model will tell us more about the consequences of these assumptions than we make, rather than telling us about the differences between those policy options and scenarios. So a very nice example, this is not from our group, but is a very interesting study, in my opinion, on looking at assessing flood defenses. And this is about coastal floods. So there is this complex model that I confess I don't understand myself very well, that looks at how waves breaks and how that impact the height of the waves on flood defenses. And these people in this study, what they did is they ran a sensitivity analysis of this key design indicator they had, which was this coastal defense vulnerability. More precisely, it was essentially the probability of the coastal defense being exceeded. And they looked at what was controlling in this indicator in their model. And they did this evaluation. So again, we have a sensitivity index. The higher, the more important an input is. And this is now tracked over time. So for example, if we follow these blue lines, it's the global sea level rise scenario. And what we see is that at the beginning of the simulation period, this is actually not very important. And then as time progresses, this becomes more and more important. And then from this moment on, it's the key control of the future coastal defense vulnerability. And one line which is very interesting to track is the red line, because this is instead the wave setup. So it's a parameter that describes the way that bathymetry influences the way that waves break. So this has nothing to do with our policy decision or future climate change. This is simply uncertainty we have unavoidably about the system setup and configuration right now. And what we see is that in the midterm, so for the first 50 years of simulation, this is by far the most important control of the model predictions. So this means that this model cannot be used really for impact assessment on these temporal scales, because the prediction would be conditioned by whatever number we decide to attribute to that very uncertain parameter more than anything else. So this is just a few examples of the kind of questions that we can ask with these methodologies. And hopefully I also gave you a flavor of how of the implications then in terms of how we develop model, how we use model, how we decide that the model is adequate to support a particular type of decision or not, and then where we should invest in the first place to make the model more accurate or reliable. I understand we taking questions later on. As I said, I'm also happy to take questions on the more technical mathematical details of the method. But now I pass on to Saskia, who has been working a bit on our project. And Saskia, you will also introduce a bit the project, right? Okay, here you go.
Cool, thank you. Yeah, so I'm just gonna quite briefly talk through an example of doing some uncertainty and sensitivity analysis on the DAFNI platform using a sort of hydrological model as the example. But
you have to use the mouse.
Yeah. Before we get into the example, just some context and a brief introduction to our project, which is, I suppose, kind of why we're here. Francesca and I are working on a DAFNI funded project, which is looking at uncertainty quantification and sensitivity analysis for resilient infrastructure systems. So yeah, our project is hoping to set the foundations for including these kind of methods to carry out uncertainty and sensitivity analysis into DAFNI, and we're hoping to be able to really demonstrate their value to the DAFNI user community. We're going to use some pre-existing packages to do this and hope to develop two kind of pilot applications, which will be in the form of DAFNI workflows, one using a water model and one using an energy model. And then the idea is that these can be used for kind of training in the future, and we hope to also be able to provide some recommendations for how these kind of things can develop in the future as well. So back to the example. The model that I'm going to use for this is a hydrological model. It's called HyMod. For anyone that doesn't know, a hydrological model basically takes rainfall and evaporation over a river basin and outputs time series of river flow. So this model is really simple. It only has 5 parameters, which kind of control this like transformation of rainfall into river flow. And so what we can do is we can use uncertainty and sensitivity analysis to investigate how the uncertainty in these 5 input parameters translates to the variability in the model outputs. And here I'm just going to consider 2 applications of the model. So I suppose depending on how you're planning on using a model, you might be interested in different outputs. So here we'll consider using the model for just designing flood defenses. So in that case, we're kind of interested in the model outputs more focused on like high flows and maximum flows. And also an application where we use the model for designing some water supply systems. So in that scenario, we're more interested in like mean flows and the water balance. So the first step is to run these Monte Carlo simulations, which can be done on DAFNI. So the first thing to do is to upload the model that you're going to use and the data to the DAFNI platform. Like some of you might be familiar with how to do this, but essentially the model gets uploaded in a kind of containerized form, and it comes with a model definition file. So what you can see on the screen here is a nice list of all the input parameters, and these are the ones that we're going to change for the sensitivity analysis. So once you've uploaded the model and the data, DAFNI has these kind of workflows, and we will build initially just a super simple workflow. All it does is run the model once using the default parameters. And we need to do that because then DAFNI has this functionality to loop over the workflow. So this is how we sample the parameter space using this loop function. So what it does is it essentially like runs the initial simple workflow again and again, and we can specify the different parameters for each run. So there's this option to choose which parameters you want to iterate, and you can also specify how you want to sample them and between what bounds you want to do that. So at the moment, DAFNI can loop 50 times over a model, and that's something that's kind of like undergoing development as well. So we're hoping that maybe in the future we might be able to loop slightly more times. But for the case of the sensitivity analysis here, what we'll do is we'll specify that we want to have 50 different versions of each of the 5 parameters between some kind of sort of reasonable parameter space that takes into account the uncertainty in determining these parameters. And then the workflow will, loop 50 times and output the data. So in this case, it's outputting a flow time series. And I've also got it to output the parameters which are associated with each run. And once the loop has been completed, there's just one more step in the workflow, which is essentially responsible for like publishing those model outputs. They all get put in the kind of data section of DAFNI. And then you can also go do this thing where you visualize the data essentially from the DAFNI platform. So there's this little button, go to visualization. And in this example, we are visualizing the outputs in a Jupyter notebook. There are like a couple of different ways you can do it, but for the sake of our project, we think the Jupyter notebooks are really useful because you can sort of like walk through the process step by step kind of thing. So we'll be using these Jupyter notebooks for our pilot applications as well as in this example. So the first thing that I guess is useful to do is to take a look at all of the kind of outputs from the model. So here there should be 50 black lines, and this is the flow output for each of the simulations using the kind of 50 different sets of parameter combinations. So essentially what you can see is that, as expected, as you vary the parameters, it sort of changes the way that the model simulates flow. So some parameter combinations lead to like higher peak flows, or there's variability here based on that. And then for the kind of two different model applications, we're kind of considering two different output metrics, I suppose. So if you consider the scenario where we're using the model to define some sort of flood defenses, then what we're interested in is the max flow. And then for the application to the water supply system, we're more interested in the mean flow. So the first kind of step for analyzing this input-output data set is to look at the relationships sort of visually between changing each of the parameters and the output of interest. So if you look at the top row here, we consider the max flow. And what you've got is you've got 5 different scatter plots, one for each of those parameters that we varied. And what we're looking for is to see whether, as we change any of these parameters, there's a clear relationship with the impact on the model output. So in the top row, there's not much going on for the first 4 parameters, but we can see for the last one, which I've highlighted, which is called RF, that there's a kind of more obvious relationship here. And it's the same process for the looking at the mean flow as the model output. Again, we're looking for a kind of obvious relationship, and I suppose the one with the most clear pattern is the beta parameter. But to kind of take this from a visual to a more like quantifiable metric, what we can do is we can calculate these sensitivity indices that Francesca was talking about before. So if you take the example where we're looking at the mean flow, and we kind of thought that there was this obvious relationship with the beta parameter, in the box plots in the top right-hand corner, you can see that, yeah, as expected, the sensitivity indices index is highest for that parameter. So it's having the most input, it's having the most influence on the output there. And this is kind of a useful step as well to sense check some of the model results. So now we can kind of think about, well, does that make sense? Is that what we'd expect? And without going into too much detail of the hydrology, this is what we'd expect, I suppose. The parameter that has the highest sensitivity index is for the mean flow, is the one that's sort of responsible for the water balance and determining the kind of, how the rainfall gets translated into the stream flow. So it's like at this point where you can also consider those kind of things. And the same kind of situation for the other model output. So here, if we consider the max flow, again, we saw the strongest relationship with the RF parameter, and that translates into kind of higher sensitivity index for that parameter as well. And again, if we think about, does that make sense? Yes, it does. This parameter is responsible for the kind of fast flow routing component, and since we're looking at maximum flows, that's going to be logical. So yeah, once you've kind of done this process, I suppose we now have an idea of if we needed to focus our efforts on kind of refining any one of these parameters, then we have an idea that, okay, if we're going to be using the model to define or to think about flood defenses, then we need to put a lot of our efforts more into this RF parameter. That's the one that's going to have the most influence. So that was just a really quick example, but we're hoping to use 2 slightly more complicated models than that one to develop these pilot applications, which will be a kind of output of our project. And yeah, ultimately, we're hoping that these workflows will be able to enable people to use these methods themselves and kind of promote this methodology. But if anyone does want to like learn more about this, or they think they have a good model where like the sensitivity analysis would be particularly useful to maybe provide another pilot application, get in touch, because we're very open to collaborating in that sense. So yeah, I think we're doing questions now. Is that right?
Yeah.
Thank you, Francesca and Saskia. That was really excellent to see the work that's happening on DAFNI, and I'm sure it'll be of great interest to the whole of the DAFNI community. So we now have a couple of questions. Lindsay, are you okay to field those questions for us?
Yeah,
to put
no
to
problem.
Francesca, please.
Okay, so the first one we have, are there any opportunities in producing generic components, best practice, universal methods, consistent outputs for applying uncertainty analysis to new models, or does each case need to be made bespoke?
I don't know if I interpret the question right, but these methodologies are generic, and I would say that also our best practice, any best practice recommendations, we have quite a few scientific and more practical papers and workflow examples that implement and showcase some of those best practices, and they are all completely generic, and so each application needs to be run. Of course, each new models needs to be subject to its own sensitivity analysis, and but the way we do it instead is absolutely generic. And this is also why I must say we haven't spoken too much about the technical details of how you implement that, because as Saskia was saying, there are a lot of toolboxes and documentation and support on doing that, and so that's kind of the easy done part. So I hope this answered the question, and otherwise please ask for more. And are we interested in more collaboration? Yes. Absolutely, yeah.
Thank you. The next question that we have, how do you produce an assessment of how accurate your uncertainty analysis methods are? With a follow-up of, would you be able to show that when the loop count is increased, that your output is now more accurate?
So let me perhaps, if I get this right. So can you see our screen? Yeah, can you see I've moved? Yeah, yeah. So obviously, so there are the sensitivity indices that we have been calculating and showing are in themselves subject to some level of uncertainty, in the sense that because they are calculated on a finite, on a number of model executions, I don't know, 50 in the case of Saskia. Obviously, we don't know, you know, had we run more model runs, would we have got a different result? So there is uncertainty of the uncertainty and sensitivity analysis. And we can check that. Actually, the toolbox that Saskia was using in her application and we are making available does that for you. It does that with bootstrapping. So that's what this slide is about. And that's also why in a lot of the examples, including Saskia's one, you don't have a value of sensitivity index, you have a range, and that's the range of uncertainty. And then we can analyze, like we do in this case, for example, how by increasing the number of samples, these uncertainty ranges around the sensitivity indices decrease. And then we can have a bit of a discussion of when it is, you know, when is that uncertainty okay and doesn't change our qualitative conclusions. In terms of demonstrating that the output gets more accurate, that's not the point, because we cannot say whether an output, all we can do with sensitivity analysis, analyze precision. So say how much the output might vary. Whether those outputs are close or not to the target, that depends on whether we have observations to compare with or not. But this is about precision, not accuracy.
Thank you. The next question, do you find you always use around 50 runs for populating the ensemble? Is that across hydrological models or also other infrastructure models? Do you linearly vary the parameters, choose them ad hoc, or sample them from probabilistic distributions?
We were talking about this yesterday, weren't we?
Yeah. Do you want to answer or shall I?
Go for it.
So the 50, magic number 50 at the moment is just a technical constraint on DAFNI, and we are actually working with the DAFNI technical team to think about what would be a good approach in the future to change that. Whether 50 is good enough or not good enough, perhaps I have addressed already in this in the previous questions. Another slides I can show you. This is from a review paper that we published a few years ago, if you are interested. And we looked at different studies published in the literature and how many model evaluation they use versus how many inputs they analyzed. And what you see very quickly from this picture is all over the places. So there is no one rule fit for all. I guess what you got to do in your own application is start with as many evaluations as you can possibly afford, and then, you know, check whether the sensitivity indices are reasonably well estimated or not. It's difficult to give recommendations a priori. In terms of how you choose how to characterize the input uncertainty, I guess that's very much a question that depends on the problem at hand. The methodology itself can handle and be applied to anything really. You know, you could have an input which, the way it is a categorical input, so it can only take up values from a list, or you could have an input which is a continuous variable, and then if you have enough information to say, okay, it might follow this probability distribution, you can do that. If you don't have that information, maybe you can specify a minimum and a maximum, and then there will be a random sampling, uniform sampling from that range. So it's very much about the problem at hand. The methodology in itself can handle different degrees of uncertainty around the uncertainty, yeah.
Thank you. How do you calculate the sensitivity indices as a function of time in the coastal defence project?
So in itself, when you do a sensitivity analysis, you calculate indices for one scalar output, but you can say, where is that? Yeah, you can think of the time series as a sequence of, at every time step, here I think it was every year, you have a prediction. You can look at the sensitivity of that prediction for that year and calculate a sensitivity index for that year, and then you just put them together and you obtain these lines. The point being that, if I go back to this slide, the computationally expensive part of this methodology is running the model and the Monte Carlo simulation. Calculated sensitivity indices is like, you know, it's a click. And so if you want to repeat that calculation for, I don't know how many, 200 times, it's a matter of fraction of seconds. And then you plot the results over time.
Thank you. Most complex models have many parameters that can be uncertain, and when estimating Sobol indices, for example, one needs to run thousands of simulations. If the model is computationally expensive, the ensemble simulations might take a lot of time. Is DAFNI able to run these relatively quickly, or are you using another technique to reduce computational time?
So these two considerations on this question while I try and retrieve. Okay, so number one, there are different sensitivity analysis methods. the one you are mentioning, Sobol method, is perhaps the most computationally expensive, but there are others who are more frugal. So for example, in this review paper I was mentioning before, we kind of created a little bit of a map of how the different methods perform in terms of number of model evaluations that you typically need versus different other characteristics that they might have. So it is possible to use more frugal methods than Sobol. Also, I think, as I was saying before in answering the other question, we also have to be careful when we talk about, oh, Sobol requires a lot of evaluations. Yes, maybe it requires a lot of evaluation to estimate very precisely with very small confidence interval the sensitivity indices, but very often we don't need that. For example, in this example, I'm comparing a case of 300 evaluations versus 3,000. And what you see is, if the original question of the sensitivity analysis was, what are the parameters that matter very little, and we can basically put at some default value and forget about them, the answer was very clear already here. Even if these sensitivity indices are very poorly estimated, there is no doubt these inputs are important and these are not. So, sometimes we can also get away with doing a bit of a frugal sensitivity analysis as long as the key message, the key answer we want from it is clear. Who cares whether this is exactly, 0.4 or 0.2. About what's going to happen with DAFNI in the future, I don't know, because I guess that's a bit of a bigger question of also, queue management on DAFNI, because you can have a model that is very fast and running, 1,000 simulations requires 10 minutes, and then you have a model that might be very slow and running 10 simulations might require 3 days. So it's a matter of more broadly with DAFNI going forward, how they're going to manage users' request. So that's a bit of a work in progress, I guess.
Thank you. I've seen recent analysis of sensitivity analysis in ML models which show big differences between different sensitivity indices, presumably because they are highly non-linear. Is there a limit to general statements we can make about sensitivity, or is it increasingly contingent?
Does that mean, is the question because like different methods lead to different sensitivity indices, values? I don't know. Because if that's the case, that's a bit worrying, because usually in my experience, even if we use different methods, where is it? There are quite a bit of review papers that have looked at if we apply different methods to the same problem, do we get similar results? And mostly they show that maybe not exactly the same, but again, the qualitative results of what matters a lot, what not matters at all is quite consistent. So if this more recent paper questions that, then I would like to see it. Instead, if the question is within the same problem and methods, we find that some input, matters way more than others, which was, for example, this case, then no, I totally agree. This is something well known. And this is actually the reason why using sensitivity analysis, because what we find again and again is that if we have a very complex model that simulates a lot of different things and has a lot of different output, but then we are interested in only one particular output metric, good chances are that that one particular output metric is only controlled by a very small subset of input. Obviously, if we were to look, it doesn't mean that everything else is doing nothing in the model, but it's probably doing something for other variables. But if we take a complex model and only extract information on one particular aspect, that is likely to be controlled by very few input. And the reason why I highlight this is because when we use model for practical application, for decision making, that is the case where we often are. Decision makers want simplicity. They don't want to see thousands of different figures and variables and things. They want, 1 or 2, 3 metrics that they will base their decision on. And then good chances are that even if the model is very complex, those 2, 3 key metrics will be controlled only by very few input. So for the use of modeling in the decision-making realm, I think this kind of methodology is very important because we need to know what is controlling those summary output.
Thank you. The next question I have, do you also work with stochastic models that give different outputs every time they are ran with the same set of inputs? Are the techniques you are developing applicable to stochastic models, or do they need to be adapted? For example, are you able to estimate the sensitivity index of the stochastic factor?
Yeah, we did some work with a model of this kind in the past. And I think in that case, what is interesting to do is to set up the analysis. We can discuss details in aside, but you can set up the analysis in a way that the inner stochasticity becomes one more input factor, which you do not sample. The sampling happens within the model already. And then it becomes very interesting to ask the question of, is that, are other parameters that we can fix and maybe we think are very important, are they actually controlling the output more than the inner stochasticity or not? So you make that, you reshuffle your input-output data set and analyze it in a way that that intrinsic stochasticity, you make it appear among the input that you, whose relative importance you are quantifying, yeah.
Thank you. There's one final question which says that you may have already answered this in a previous answer. Is there a relationship between sensitivity analysis and dimensionality reduction? Can you simplify the model by eliminating least significant parameters?
Yes, even if this goes back to the question we were answering before, that if you isolate one specific model output, you will see that probably it's controlled by very few inputs. So that would make you think, okay, then I can reduce my model complexity. But then actually, if you do that, you're probably gonna miss out on some other output. So what people do, for example, sometimes this is an example where we have different output variable and the input. And then you have sensitivity is now, depends on the color. So when you have, like here, an input which has an entire white column, that is telling you that input is not having any particular impact on any of the output. So that could be a candidate for simplification of the model. But as you can see already here, that they are quite rare. There are otherwise always the input is doing something on some output. But that would be the connection, I guess. This kind of sensitivity analysis might give you a hint of what are components of the model parameter of the model that are not really doing much on a set of output of interest.
Thank you. That's all the questions that we have.
Well, thank you very much. I think that was really interesting, all these questions. There's a lot of food for thought there, Francesca and Saskia. And thank you for taking the time to attend, and to our two speakers for a great presentation. This webinar is being recorded and will be shared afterwards across the DAFNI community. And if you're interested in booking for further events, I've shared a link on the chat for everyone. There are a number of these talks coming up on different projects on DAFNI, and we also have a DAFNI conference on the 10th of September. So we'd really like to see you there in person. So once again, thank you ever so much. And that was a great talk. Thank you both.
Thank you for having us, and get in touch. Our emails are there. So thank you.
Bye.
Bye-bye.